Hello, in this video I'm going to talk about hypothesis tests for the population mean. So the way that any hypothesis test works is that we start out by writing a pair of hypotheses, a null hypothesis and an alternative hypothesis. So these will take hypothesis. The null hypothesis, we use the symbol H with a subscript of 0. We call that H naught. And if we're doing a test about the population mean, the null hypothesis will be that the population mean is, I should have put a colon there, is a certain value. And our alternative hypothesis, which will use either an H with a little subscript of 1, sometimes you'll see an A or an alpha there, but that would be that the mean is something different than what was proposed in the null hypothesis. Either that the mean is less than this amount, or it may be that we say that the mean is greater than the amount proposed in the null. And a third option would be to say simply that the mean differs from the amount that's stated in the null hypothesis. So the way that we set this up and which of these three options we choose is important. If we have a theory that the mean is less than some assumed amount, then we end up conducting a left-tailed test. If in the alternative hypothesis we are theorizing that the mean is greater than said amount, then we end up with a right-tailed test. And if we are simply saying that the mean differs, but we're not sure whether it's less than or greater than, we will conduct a two-tailed test. So I'm going to just jump in with an example, and let's say, for instance, that you have read over a manufacturer's claim that the battery life for a cell phone is about 10 hours with normal usage. And maybe you're not buying this and you think that actually the battery life seems to be less than that. So you might be interested in conducting a left-tailed test. So if the manufacturer claims that it's 10 hours and your theory is that it's less than that, then this would be what your pair of hypotheses would look like. That the mean is 10 hours, and the alternative would be that the mean is less than 10 hours. We're going to give the company the benefit of the doubt and assume that what they say is true, and that's why that is the statement in the null hypothesis. So the alternative hypothesis is sometimes called the research hypothesis. So this is really the researcher's alternative to sometimes what we call the status quo. It's a challenge to this, in this case, which would be a claim or a prevailing assumption. So in order to test our theory, we're going to gather evidence. And this is in the form of sample data. So it's important that we take a random sample, and we want to make sure that that random sample comes from a normal population. And you can check this by looking at a normal probability plot, or maybe in conjunction with a box plot. We also want to make sure that there are no outliers in the data. Now, if you are not able to confirm that the data comes from a normal population, the alternative is you can make sure that you take a large sample. Now, large, for the type of test that I'm going to propose, is not all that big. Just a sample size of at least 30 will do. And we want to make sure that these values in the sample are independent. So as long as we can confirm these three things in our part of our process, then we're going to be good to go with this strategy. We're going to use end up using a t-test. But let's just, I want to give you an overview, just a general idea of how this is going to work. So if our evidence is coming from a normal population, and we take a sample. Since we're testing on a theory about the mean, what we're really going to be interested in is the result that we get from our sample. In other words, the sample mean. So it turns out that this sample mean should, under these conditions, well, if we have to calculate and use the sample standard deviation, a standardized version of this statistic is going to follow a t-distribution. And the t-distribution is bell-shaped and centered at 0. So that's once we standardize. Now, but just to picture this, I want you to think that if this was just a sampling distribution, and we're assuming that this statement is true, that the mean is 10, then we would expect the sampling distribution to be centered at 10. And I'll point out the difference here. I'm going to put a 0 here. When we standardize it, that would correspond to a t-score of 0, wherever this center is. Now, let's say that we gather sample data, and we find that our sample mean is maybe like a 9.8. And we're wondering if this is sufficient evidence to contradict the claim that the mean is actually 10. Well, when we're taking samples, we expect there to be some variety from one sample to the next. And so it might not be all that unusual to get a sample mean of 9.8 when in fact, the true mean is 10. So how much variety that we would get from one sample to the next, though, depends on the standard error of the mean. And so that is measured by taking s over the square root of n, our sample size. And just for this example, I want to just say, assume that this standard error of the mean is maybe 2. And so if we think about what that tells us, now I'm taking a little bit of liberty here and treating this like it's a normal distribution, but just to give you an idea, that would mean that we would have, roughly a distribution that looks like this, where these inflection points are at one standard error on either side of the mean. So now when we're using a t-distribution, that's not exactly accurate, but it's sufficient for us to just get an idea of how the test is going to work. So when I get a result of 9.8, that's actually really close over here to the assumed mean of 10. And so that's probably not going to be sufficient evidence or convince me that this statement was anything but true. In fact, that might even confirm to me that maybe the mean really is 10 hours. Now, certainly if I get a result over here, anything on the right-hand side, maybe like even say 11.3, well, that's certainly not going to convince me that the mean is less than 10 hours. So when I said that this is a left-tailed test, when I'm conducting a left-tailed test, I'm really looking for evidence over here in the left tail. So let's take in one more scenario, and maybe I get a sample mean of 6.3. And I say, well, where does 6.3 lie in this distribution, this assumed distribution? So that's over here in this left tail. So certainly that is a value that's less than the assumed mean of 10 hours, and it's over here in the left tail. But my question is, is this just by a chance that I happen to pick a sample where I had a really low mean? So I'm wondering if this is different enough, in this case low enough, for me to dispute this claim that the mean is in fact 10 hours. So what I need is some sort of a cutoff point. I like to call it just a line in the sand, and if I get a value that's below that line, I'm going to say that that is sufficient to contradict the null hypothesis. In the language of hypothesis testing, we would say that we could reject the null hypothesis. So again, if I get something close to 10, I'm probably going to say that one is not sufficient evidence, and certainly if I get anything more than 10, that's not going to convince me that it's less. So I'm looking for a value that's way less. And so in the next video, I'm going to talk about how we can draw this line and where we should place that. So if we cross the line, we're going to reject the null, but if we are to the right of that line, we will fail to reject the null. Okay, so join me in the follow-up.